Alright, so in this video we're going to talk about logarithms. The thing about logarithms is they tend to seem a little bit worse than what they actually are. Because you see notations like log with a subscript of 2 and a number inside and probably wonder what on earth this means. So really it all comes down to the question of exponents, because at the end of the day, exponential expressions and logarithmic expressions are like salt and pepper. They go together one on one. So suppose I have a raised to the x power is equal to y. And then further, suppose that I know the value for a and the value for x. It's really easy to find out what y is at this point. If x is an integer, then I just multiply a by itself x times. And if it's not an integer, well, I can use a calculator for it. But the actual value y is easy to find conceptually. I just take a, raise it to the x power, and throw it into a calculator. Now suppose that I start with the same equation, a raised to the x equals y, but the information I have is different. Suppose that I know the value of a and the value of y, but now I need to figure out what power of x got me there. And at the end of the day, that's all the logarithm really is. It's trying to figure out what exponent gets you from what base to what value. We have special notation for this. We say that the log with the base of a of y is expressed as the symbols log with a subscript of a for your base. You input y, the value that you're trying to get to, and then what you get as an output is the exponent that you're looking for. And this corresponds to the original expression a to the x equals y. So at the end of the day, when we say log base a of y, we're simply just trying to find the mystery exponent x, such that a to the x is equal to y. Again, this is one of those things where the notation makes the concept seem a lot worse than it actually is. All the logarithm is trying to do is tell me what exponent I need. In the next slide, we'll look at a couple of examples. We'll look at things exponentially or in exponential notation that we're used to, and then we'll convert it to this new logarithmic notation. So in the following 4 examples, the goal is to find the mystery exponent. We're going to look at 2 to the y equals 8, 3 to the y equals 1 over 81, 2 to the y equals square root of 2, and 125 to the y equals to 5. And our goal is to find the value for y that correctly fits each one of these. I encourage you to pause the video and try to think about what values that you can plug in for y that make each one of these statements true. Alright, once you've thought about it for enough, we'll see that for expression a, that y equals to 3 makes this true, because 2 to the third equals 8. For expression b, a value of y equals to negative 4 will be the one that works. And then for c, y equals to 1/2, and for d, y equals to 1/3. I suggested going back and looking at the section 1.2 video again because the logarithm and exponential chapter definitely has a lot to do with exponents, and it's good to know how these properties work. In each one of these places where I'm seeing a fraction, recall that that corresponds to a negative exponent, and each one of these places where I'm seeing a radical, that corresponds to a fractional exponent. But for each one of these expressions, a through d, we found the mystery power that takes us from a base to get us to a final value. Now let's take all this information and convert it into logarithmic notation. The expression 2 to the third equals 8 translates into log base 2 of 8 equals to 3. For the second expression, we get log base 3 of 1 over 81 equals to minus 4, log base 2 of the square root of 2 equals to 1/2, and log base 125 of 5 equals to 1/3. So it's totally okay if this is the part of the video where things are starting to seem a little bit weird, because we're trying to take this concept of finding the mystery power and putting a precise notation on it. But let's really dive into what's going on, especially with that first example. When I know that 2 to the y equals 8 gives me a y value of 3, I can reframe that into the problem of log base 2 of 8 equals to 3. So when I have a log base 2 and the input value of 8, the answer is what exponent brings me from a base of 2 to a final value of 8. So when I see the symbols log base 2 of 8, it's just asking what exponent do I put on top of this 2 so that I get 8 as a final answer. And that's really all the logarithm is. And the same rule applies for the other 3 examples. Note that the logarithm does follow a couple of rules. The first of which is the following. Log base a of y requires a base a which is bigger than 0 and not equal to 1. So it's the same conditions that I would put on the base of an exponent. Log base a of 1 always equals 0 because a to the 0 equals 1. Lastly, log base a of y is undefined if y is something equal to 0 or less than 0, because we know a to the x is never equal to 0 itself, and it is never negative no matter what I put in for the exponent. Now let's look at the general rule. Take a base of a that is bigger than 0 and not equal to 1. The logarithmic form is log base a of y equals to x, which only happens if a to the x is equal to y. This gives us a nice way to transform from one form into the next, because when I look at symbols like log base 3 of 27 equals to x, this can be a little bit hard to do in our heads, even if we understand that we're just trying to find this mystery exponent. So what we do is we convert it into exponential form, so it's a little bit easier to see what that value of x should be. So I get 3 to the x equals to 27. And now I just realize, since 27 is a power of 3, I just have to put in the correct exponent of x, which is in fact a 3. This tells me that log base 3 of 27 is equal to 3. Alright, so now we're going to compute the log base 12 of 2 times the square root of 3. In other words, we're going to figure out what that x value is. Like before, let me take this and turn it into exponential form. This will become 12 to the x equals 2 times the square root of 3. So unlike the previous problem, this one's a little bit less obvious in terms of what that value of x should be. So I'm going to start playing with the exponents on the right-hand side a little bit. I'm going to rewrite the square root of 3 as 3 equals to 1/2. Also realize that 2 I can replace as 4 to the 1/2, because when I take the square root of 4, I get a 2. Now since I have a product and two terms raised to the same exponent, I can multiply them inside and bring that power of 1/2 to the outside. That is, I can rewrite this expression as 12 to the 1/2. This means that 12 to the x equals to 12 to the 1/2 can only result in x equaling to 1/2. Therefore, log base 12 of 2 times the square root of 3 is equal to 1/2. For our last example, look at log base 2 of 1 over 32 equals x. Let me turn this into exponential form, which gives me 2 to the x equals 1 over 32. At this point, we should be able to recognize the number 32 as a power of 2. So I'm going to rewrite the right-hand side as 1 over 2 to the 5th, or 2 to the negative 5. This tells me that I get an x value of negative 5, so the log base 2 of 1 over 32 has to be equal to minus 5. So computing simple logs like the ones in this slide and the ones in the previous slide really come down to playing this game with exponents. You're trying to get bases to match to figure out what that mystery exponent has to be, and once you've done that, you have found the logarithm of certain values. The last thing we'll talk about are a couple of cancellation laws. The first is that log base a of the exponential a to the x is just equal to x, and the exponential a raised to the log base a of x is just equal to x. Essentially what we're getting at is that logarithms of base a and exponentials of base a are polar opposites. They cancel each other out, leaving behind whatever was inside. And this only works when I have like bases across all terms. So if I have log base a and inside is an exponential with the base of a, then I get a nice cancellation. Same thing, if I have a raised to the log base a of something, then those two things cancel out because everything therein is going to have the same base. However, if I had something like log base 2 of 3 to the x, I would no longer get a cancellation because I don't have like bases. So it only works if the setup has all bases in the exponential and the logs being the same. Let's look at a couple examples. Consider log base 5 of 25. This is asking for the power of 5 that gets me 25 as an answer. And when we think about that long enough, we realize that I should get the number 2 as a result. But let's try to transform this expression so that that term inside looks like an exponential. I can rewrite this as log base 5 of 5 squared. Now I have a log with the base 5 and an exponential with the base of 5, and our first cancellation law says that these need to undo one another, so I just get left with the exponent, which is 2. For our next expression, look at log base 16 of 4. And immediately I can take that 4 inside and rewrite it as the square root of 16. Now I'm starting to get some numbers that match up with one another. And further, as we've seen a couple of times in some examples, I can take that square root of 16 and rewrite it as 16 to the 1/2. Now that I have a log and an exponential with a base of 16, Those two things cancel each other out, and I just get left with the exponent of 1/2. For our last example, we'll look at log base 1 over 9 of 3. I can rewrite that 3 as the square root of 9, kind of like I did in the previous example with the 4 and the 16. Further, I can take that 9 to the 1/2 and rewrite it as 1 over 9 to the negative 1/2. I'm forcing that negative in there so that I can make that inside look like a fraction so that my bases match. And now that the bases match, my cancellation law takes over and I just get left with the final answer of negative 1/2, and we're done. Thank you so much for watching, and join us in our next video on logarithmic functions and their graphs.